Let's begin our journey into the world of fluid dynamics with the Navier-Stokes equations. These equations, named after Claude Louis Navier and George Gabriel Stokes, are the mathematical backbone for describing the motion of viscous fluids. They express how fluids like water and air move, taking into account viscosity, pressure, and external forces. At their core, the Navier-Stokes equations are a set of partial differential equations that balance momentum and conserve mass in Newtonian fluid. This means they help us predict how fluids will behave in countless scenarios, from the flow of air over an airplane wing to the movement of blood through veins. What makes these equations so fascinating is their universality and the fact that, despite their widespread use in engineering and science, some of their deepest mathematical properties remain unsolved mysteries. Navier-Stokes equations aren't just theoretical, they're at the heart of real-world applications. Engineers use them to design safer cars and more efficient airplanes, while scientists rely on them to study weather patterns, ocean currents, and even blood flow in the human body. These equations are also crucial in analyzing pollution, designing power stations, and understanding phenomena like turbulence. Paired with Maxwell's equations, they form the foundation of magnetohydrodynamics, which explores the behavior of electrically conducting fluids. Yet despite their practical power, the equations are notoriously difficult to solve, especially in three dimensions. This complexity is why the Clay Mathematics Institute has listed the Navier-Stokes existence and smoothness problem as one of the 7 Millennium Prize problems, offering a $1 million reward for a solution. Solving the Navier-Stokes equations means finding the flow velocity, a vector field that tells us the speed and direction of fluid at every point in space and time. Once we have this velocity field, we can derive other important quantities like pressure and temperature. Unlike classical mechanics, which often tracks the position of particles, fluid dynamics focuses on velocity fields, making it more suitable for visualizing how fluids move. For example, streamlines show the paths that massless particles would follow, revealing the overall behavior of the flow. In practice, exact solutions are rare and usually limited to simple cases like laminar flow between plates. For more complex or turbulent flows, scientists use numerical methods in computer simulations such as Reynolds averaged Navier-Stokes (RANS) or large eddy simulation (LES) to approximate solutions and gain insights into real-world fluid behavior. Despite their power, the Navier-Stokes equations present significant challenges. Their nonlinearity, especially due to convective acceleration, makes them difficult to solve analytically. This complexity is most evident in turbulent flows where chaotic and unpredictable behavior emerges. While simplified forms of the equations can be solved for specific cases, the general three-dimensional problem remains unsolved. Existence and smoothness of solutions in three dimensions is one of the most important open questions in mathematics today. In practical terms, this means that for many real-world problems, we rely on approximations and computational models. The quest to fully understand and solve the Navier-Stokes equations continues to drive research in mathematics, physics, and engineering, promising new discoveries about the nature of fluids and the universe itself.